All right, we're going to get going. And so, good afternoon, everyone. And I'd like to welcome you to the third session in our Tribal Wastewater Operator Certification Series. And today we're going to be talking about wastewater collection systems and mechanical systems. Okay, real quick about who we are. We're the Southwest Environmental Finance Center. We're part of the UNM School of Engineering here in Albuquerque, New Mexico. That's us in the School of Engineering Centennial Engineering Building. And you can see it behind me as well. Partners on this project are also Wichita State University Environmental Finance Center. They also operate the Heartland Environmental Justice Center, and they're doing training and technical assistance as part of this work that we're doing. And they're located in fabulous Wichita, Kansas. All right, I'm Matt Ziegler. I'm the Tribal Water Utility Program Director here at the Southwest Environmental Finance Center, and I work with a lot of you in EPA Region 6 on drinking water issues, but also working with your tribal nations on wastewater issues.
And I'm James Markham. I'll be doing part of the training today. I'm a research engineer here and I do training and technical assistance as well.
And real quick, we're here today as part of our tribal wastewater program, and it's all about assisting tribal nations in EPA Region 6, 7, and 8. We help you with training like this today, and we do technical assistance to help you prevent, reduce, eliminate pollution. And we're helping to enable our communities comply with environmental regulations and build your internal capacity to sustainably operate and manage your wastewater infrastructure. And we want to make sure part of our program is making sure that you have the wastewater facilities that your communities need. And so that's helping you access public funding to build the infrastructure you need. And it's all about protecting both public health and the environment. And if you want some more information about our program, there's a quick reference code there. It's not going to be up long enough, but we'll go ahead and send out that information as well after the webinar. And real quick, the program services we offered, we already covered it a little bit. We look at wastewater needs, both capacity needs and infrastructure needs. We help you find the funding you need to build it. We do training, and we just started some peer-to-peer learning series. So watch out for more information on those. So this is our Tribal Wastewater OpCert series. We're in session 3. We're meeting every fourth Wednesday to do another part of this series. And today we're looking at collection systems and mechanical systems. And next 4 weeks, we'll look at preliminary treatment. And I'd like to hand it off to James to talk about collection systems.
Okie dokie. I am going to turn my mic or my video off just because I find it incredibly distracting to see myself talking. So today we're going to be talking about collection systems. Wastewater obviously has to travel from your customers to whatever treatment facility you have, and it does that through what's called a collection system. For many of you, this is going to be review, but if you're sort of newer to the wastewater game, hopefully we can give you some basics on how collection systems operate, and most importantly, the kinds of things that you're likely to see on a certification exam. Obviously, we can't cover every detail and everything there is to know about a collection system in an hour or so, but the idea here is to give you an overview, touch on some of the more important aspects, the things you're going to need to know for a certification exam, and as always, we encourage you to review whatever jurisdiction-specific study materials you have. As Matt said, we're sort of broadcasting this across a wide variety of states, and there's a lot of different certifying agencies. All of them have study materials. So pay attention to what we're showing here, but also compare that to the study materials for your jurisdiction, because there might be differences in typical construction techniques in your area versus what we discussed today. But again, today is about getting you familiar with terminology, some basic design elements, so that you have a broad understanding of collection system details and components. There are 6 basic topics that we're going to cover today and that typically show up on the operator's exams. Cleaning and maintenance is a big piece. Lift stations, we'll go into what those are in a bit. Manholes, maps, piping and joints, and then the service connections. We're going to cover these topics today, but we're going to do them in a slightly different order. We're going to kind of start with a broad overview and then narrow down to some of these individual topics. And the first thing we're going to start talking about is basic design elements. You kind of need to know how a collection system is set up in general terms, even if the particular system that you work on maybe doesn't have all of the components that we're going to be talking about today. You can kind of think of this next section as an overview and a review of vocabulary terms and basic building blocks that you'll need to know to talk about sewers and to take the exam and to understand the questions that you're liable to get asked on the exam. So what we've got here in this picture are a bunch of orange blocks that represent buildings, a big blue block that represents the wastewater treatment plant, whatever kind of plant that might be. And basically what we're going to discuss is how the wastewater gets from those individual locations, those businesses, houses, neighborhoods, to the wastewater treatment plant. We're going to work our way essentially downstream because mostly what we're talking about today are gravity-fed sewer systems. So we're going to sort of start at the high point and end at the low point, which is the wastewater treatment plant. The pipes are typically going to get larger and larger the closer you get to the wastewater treatment plant, and they're typically named for the task that they do. So working downstream from the customers, the first thing that you're going to have are building sewer or service lines that go from the houses and structures, typically out into the front of the middle of the street. In your location, it might be into an alley. My particular house, the water pipes are in the front of the house. The service lines for the sewer happen to be in the back of the house. But those all join up to what are called laterals, which are slightly larger pipes that collect sewage from the individual houses and transport it further down the collection system. So each lateral will typically have multiple buildings connected to it, and the laterals themselves will then connect to main sewers. And these are typically the sewers that are going to be running down the middle of larger streets. They collect the flow from the laterals and branches. They take that flow to what are called trunk sewers. These are even bigger lines. They're the main arteries that convey wastewater to what is often called an intercepting sewer. Sometimes there's a lift station in between the intercepting sewer and the treatment facility. And the lift stations do exactly what they're named. They lift waste up, because if we've got a gravity system and the sewage is flowing downhill, at some point we're probably going to have to lift it back up to get it to the actual treatment plant. So this is, of course, kind of an idealized system. Not every collection system has a layout exactly like this. Some larger systems may have something that looks exactly like this, and other sections that look a little bit different. One thing you're liable to run into, particularly if you have lower lying neighborhoods, maybe neighborhoods that are lower than the wastewater treatment plant, are neighborhoods that are connected to this via lift stations, because you have to pump the sewage uphill. So if you've got, for example, a neighborhood that is at a lower elevation than the wastewater treatment plant, you would have building sewers and laterals and maybe even a main that are connected to that. But at some point, we've got to push that sewage uphill. So we'll have a lift station. And the thing about lift stations is, although the feed into the lift station is by gravity, there are pumps in there that push the sewage out. So you're going to have what's called a force main. So typically when we're talking about sewers, we're talking about gravity sewers, where gravity's doing the work for you. If something is going to be connected to a pump, they use the term force main, and that is a specific kind of pipe that basically goes from a lift station to its final destination. Some basic information that you need to know about gravity sewers in general. If you look at the as-built for your particular system, you might find that things do not move in straight lines because we're using gravity here. The slope and the paths that various sewer lines take often follow the lay of the land. In order to get the sewage from point A to point B, we try to design sewer systems to have a flow of somewhere between 2 and 8 feet per second. So that's how fast the sewage is moving through the system. The ideal velocity is 2.5 feet per second, which is called scouring velocity. Basically, the idea here is that we want the water to move fast enough so that the solids that are mixed in with it make their way to the wastewater treatment plant. If water is moving slower than 2 feet per second, solids will settle out. They'll block up the pipes, which is something we don't want to have. So we're looking for that 2 to 8 foot range. Those are good numbers to memorize, with 2.5 feet per second being ideal. Again, since we're using gravity to move sewage in most cases from point A to point B, we build a slope into the pipe so that the pipe is running downward, and we design the slope to keep that minimum velocity of 2.0 feet per second. When we're doing this design, obviously, over the course of the day, the amount of sewage that's moving through the pipe changes, it ebbs and flows. So we're designing for what's called the peak flow, or the maximum expected flow. Sometimes that is, we're looking at the flow max during a day, but sometimes systems will be built with growth in mind. So you might have a wastewater treatment plant and a sewage plant collection system that has a greater capacity, design capacity, than what you're actually using it for, with the idea that the community is going to grow into it. So one thing to kind of know when you're thinking about your own system is what the typical per capita flow is in your system, and in your area. When the tests are being put together, they will often look at the typical per capita flow in your jurisdiction. And that's going to vary whether you're in an urban area versus a rural area, and it can vary from state to state. So it's a good number to know. The volumes are going to vary, but again, that's information that your testing agency can provide to you. However, there is one max flow that is pretty much consistent, and that's sort of when the most flow is going through a typical sewer system during the day, and that's typically between 10 a.m. to noon. And if anybody knows why that is, feel free to throw that into the chat. Why do you think that the typical max flow might be in that 10 to noon range? Yeah, well, the reason that it happens around 10 a.m. to noon is because most of us tend to go to work at around the same time in the morning. So people get up, take a shower, have breakfast, maybe do some laundry. It's that morning flow that we all create that's working its way through the system in that 10 to noon range. So that's another number to sort of commit to memory when max flow typically happens. Another thing that is really important to know is how wastewater treatment plants are sized. So how big, how much capacity a wastewater treatment a plant can take. And typically that's somewhere between 2.5 and 3.5 times your average daily flow. And the reason we do that, of course, is because, an average is exactly that. An average, sometimes the flow is going to be higher, sometimes it's going to be lower. So we want to make sure that the wastewater treatment plant is built with growth in mind, but also so that it doesn't get overwhelmed at any point during your use. In your typical sewer, as I said, you're trying to maintain that 2 to 2.5 foot per second velocity, and you do that by sloping the pipe so that the water travels downhill. Design requirements vary from jurisdiction to jurisdiction. So this is, again, something that you want to look at for your particular location. But this is an example from the state of Michigan. This is specific to mobile home and seasonal mobile home park sewer designs. They have a design requirement of 2 feet per second at design flow. And the important part about this slide is the table at the bottom. And what it basically shows you is that the smaller the pipe, the steeper the slope has to be to maintain that scouring velocity. So you can see here for a 4-inch pipe, we've got a drop of about 1.2 feet every 100 feet, whereas for 14-inch pipes, we've only got a drop of about 0.7 feet. 0.17 feet per 100 feet. But what you can see, if you're looking at, average of 6-inch or 8-inch pipe out in the streets, couple of 100 feet gets you buried down fairly quick, fairly deep in the ground, and excavation is pretty expensive. So this is one of the reasons that we end up having lift stations, because you can't just keep digging down. After a certain point, it becomes more economical to install a lift station, push the sewage back up to the surface or near the surface, and let gravity take back over again. So again, design requirements can vary by jurisdiction. This is where your local materials are going to come in useful. And it's important to know the per capita flow in your particular state. It's something that is often asked. In New Mexico, the per capita flow ranges from 60 to 125 gallons per day. Most of the design requirements are based on those flows, but in Michigan mobile home park sewers, they actually have a flow per day per home site. So they're not looking at per capita or per person flow, they're looking at per home site flow. So a good thing to look at as you're going through your study materials as are what the specific design requirements are in the jurisdiction that you're going to be taking your test in. Couple of other things to recognize about gravity sewers is that the pipes have to be sized for available cleaning equipment and vice versa. Every sewer is going to get blocked at some point. You want to be able to be sure that you can clean them out. And so as you're adding stuff or pipes to your network or as you're buying equipment, it's really important to make sure that they match each other. Another interesting thing about gravity sewers is that the pipes are never full, or at least they shouldn't be. Typically, they flow about half full during average daily flows. So at those high points, they shouldn't be filling the pipe up entirely. And you want them to have some air room in there for two real reasons. One, you want to have room for air, so if there's a high flow day, that the pipe doesn't become pressurized. But you also want to maintain aerobic conditions in the pipe. So there's bacteriological activity going on in the sewage as it's moving through there. The last thing you want is your sewage to turn septic, to go anaerobic before it gets to your treatment plant, because if that happens, and this sometimes happens when there are blockages and the sewage just sits in pools, you can get anaerobic conditions, which then can make the treatment at the wastewater plant really problematic. And we'll talk a little bit more about that a little bit later on. Gravity sewers are typically in the 4 to 8 foot depth range, but they can be a lot deeper. Kind of depends on the specific situation and the economics. I live in Albuquerque. The lateral behind my house that my service line connects to is easily 15 feet down. I was really surprised when they replaced our sewer that it was down that far. So typical depth is, in the 4 to 8 foot range, but again, particularly on a very long trunk line, it might be significantly deeper. Physically, where they're located, it's typically in the middle of the street, which is why when sewers get replaced, they have to, tear the streets up. Laterals, mains, and trunks typically in the center of streets. Sometimes the laterals will be in alleys behind streets. That's the case in my particular neighborhood, but it's not common in the rest of Albuquerque. Because we often have water lines in the streets near our sewer lines, we want to make sure we don't get any sort of cross-contamination. And one of the ways that we help prevent that is by making sure that sewer lines are buried below any existing water lines. So they're typically at least 2 feet below water lines and 4 feet horizontally, so either left or right of water distribution lines, just so that you can avoid any potential contamination if there is a break. So that's sort of a basic overview of design elements and how these are basically laid out. Now we're going to sort of get into the nitty-gritty a little bit more and talk about the materials that sewer lines are made out of. Specifically, we're going to talk about piping and joints because, again, these are things that you'll need to know in the course of your work, and also are topics that typically come up on wastewater treatment exams. From a design perspective, when they're selecting pipe, what you're looking for is resistance to deterioration, the ability to withstand surface loads. The sewer pipes are often buried in the middle of the streets where trucks and cars are moving across them. So you want to have the ability for them to not crack under pressure. Resistance to root intrusion is really important as well. Sewers are constantly flowing with water. Trees love that. So if there are gaps, the trees will find it, and that can block up your pipes and damage things. Um, you want the pipe material to be able to minimize leakage because, again, leakage often leads to root intrusion and other kinds of problems. And then, of course, cost and service lifespan are important factors, right? You want to get the most money or most bang for your buck. And ideally, we're building for 50, 60, 70-year lifespans, although it sometimes doesn't work out quite that well. So let's start with pipe materials and the kinds of materials you're both likely to see in your day-to-day work and the kinds of pipe you're going to likely to be asked questions about on the exam. There's 4 basic categories. You've got cement kinds of pipes, you've got metallic pipes, you've got vitreous clay, and you've got different kinds of plastic. So asbestos cement, which isn't really used anymore, but there's a lot of it out there. Reinforced concrete and regular concrete pipes fall into that cement category. Cast iron and ductile iron were popular quite a while ago. So you're liable to run into a lot of that. Those are our metallic pipes. Vitrified clay is its own thing. This is often seen in older houses in service lines, sort of running from the house to the lateral. But there are also older systems that have vitrified clay, large diameter pipes in use as laterals as well. And then we've got our plastic pipes, the more modern stuff, fiberglass reinforced pipe, ABS. This is the stuff that you can see at Home Depot quite often. It's black, typically acrylonitrile butadiene styrene, and then HDPE and polyvinyl chloride. And each of these has pros and cons and is used in different kinds of applications. And they are joined together differently. And how the pipes are joined is something that is really important to know. But let's talk a little bit about sort of the pros and cons of each of these materials. Asbestos cement was kind of a big deal for a while. Not really used anymore because of the asbestos side of things, but you're able to run into it. Reason it was used, it's really resistant to deterioration by most of the things that you'd find in wastewater. It's really stiff, it's rigid, so it could withstand loads pretty well. That being said, like most cement and metallic pipe, it's subject to something called crown rot, which is the upper part of the pipe being corroded by hydrogen sulfide gas that combines with moisture in the pipe to form sulfuric acid. And over years, that can eat away at the pipe. So if you're ever doing a repair and you see a situation where the bottom of the pipe looks pretty solid, but the top is thin, maybe crumbling, that's crown rot. And that is something that cement and asbestos cement pipe can have happen to it. Obviously, because of the asbestos content right now, its use is restricted by OSHA. So you're not going to be installing this, but you might be working on it. The joints, so how these pieces of pipe are fit together, are typically rubber gasket couplings and rubber sleeves. The pipe's straight, doesn't bend very well, so we tend to use gaskets and sleeves to join the pieces together. And sometimes you'll see these sort of small sections going around corners. The other sort of 2 main cementish pipes are reinforced and non-reinforced concrete. You'll typically see these out in the larger diameter pipes running in the streets. We've got a couple of examples that we're showing you there. The reason that they're used is they're really, really rigid. They can withstand really high surface loading. The ones we are showing in this picture right here, you can see they're bare on the inside. So there's no coating, but like asbestos cement pipes, these are subject to crown rot. So sometimes you will see these kinds of pipe segments with a plastic lining or an epoxy or coal tar lining on the inside to help protect the pipe from crown rot. You can actually see there's 2 kinds of pipe showing here. We've got the cement pipe in the front and the green PVC pipe in the back. Um, the joints on these are typically rubber gaskets, bells, and spigots. So this front end, small end here on the left side of the picture, that's the spigot. And the other sort of wider flared out end, that's the bell. There's a rubber gasket that goes around the spigot, and when you stick the two together, they become basically watertight. Sometimes they'll use a bituminous material in there, but the idea is that there's a gasket in between each of the sections, and that's what keeps it watertight. You may run across cast iron and ductile iron pipe, particularly in older sewers. It's really, really rigid, can resist high surface loads, typically very expensive. It's often required for bridge crossings or in areas where the lines are shallow and very close to the surface. There's a couple of different ways these pipes are joined together. Um, Typically, it's some kind of rubber or caulk gasket or a mechanical push-on type gasket, or it might be a bolted flange like we're seeing here. On really old installations, you might actually see sort of a bell and spigot that has lead poured into it as well, which is also potentially hazardous material when you're working with it, so something to be aware of. But that is one way that these pipes, these metallic pipes are joined together. This is a really oddball looking pipe in this picture here. It's really hard for me to find pictures of good cast iron pipe. This happens to be from a bridge crossing in Manchester, England. It's rectangular, which is kind of unusual. Typically they're round even in bridge crossings, but you might run across something strange like this. Then we've got our vitrified clay pipe. Typically in current installations, it's going to be used for smaller diameter pipe. It's very rigid, but it is subject to cracking from root intrusion. It's very resistant to acids and caustics and solvents and gas. It's basically pottery. The joints, and you can kind of see both ends of a typical vitrified clay pipe here. They will have polyurethane or PVC compression ring gaskets. So you can see the narrow end has a ring on the outside, the bell end has a ring on the inside. You slip those two together, they form a tight joint. Again, with older installations, particularly on service lines, you might see mortar joining these two together, these two ends together. Moving on to plastic pipe. We've got fiberglass reinforced, as you can see, comes in a wide variety of diameters, could be anything down to about 6 or 8 inches or up to 24 or more. One of the nice things about this is it's semi-flexible, so there's a little bit of give to it, and they're fairly corrosion resistant. There's some indication that they're subject to crown rot, but it's typically not that big of an issue. Like some of the other pipe we've looked at, the joints are typically rubber gasketed bells and spigots. That phrase is something to remember because it's sort of the most typical kind of joint. But like most plastic pipe, this kind of pipe, this fiberglass reinforced pipe, is potentially subject to failure from unanticipated surface loading. So if it's installed incorrectly, or if it's subject to much higher surface loading than the original design called for, you can have issues with pipe cracking and collapsing. Moving on to the other more sort of typical plastic pipe, we've got the ABS. It's really flexible. It's resistant to almost everything that you find in wastewater, but petroleum products can soften and erode it. This is one of the reasons you don't want to pour oil and gasoline and that kind of thing. Solvents into your drains. You'll often see these used for service lines, but also for bigger lines because you can essentially weld the ends together. So sometimes you'll see joints that are solvent welded or gasketed bell ends. Because it's plastic, and plastic just means, deformable, it really requires careful installation and inspection because if it's not installed correctly or if it's subject to really high loads, it can flatten out, it can turn oval, and that in turn negatively impacts the flow, can cause blockages, things like that. Our last two kinds of pipe are HDPE and PVC. They're both really flexible. They're both durable, resistant to most stuff. HDPE, again, often used if you've ever had or seen a sewer line being burst and replaced. where they basically pull a cable through it that breaks the old pipe out and pulls a new one through. That's often HDPE pipe. You can thermally weld this together. So often you'll see in very long sections kind of a ring around the pipe where two sections are welded together. It's typically used for small diameter pipe and for low pressure sewers and force mains. And then PVC, this is kind of the standard that you see pretty much everywhere. It's used for water pipe and wastewater pipe. They're just different colors typically. It's flexible, resistant to corrosion. Typically also use that rubber gasket and bell spigot, gasket bell and spigot joints, which you can see in the image here. You see the bell with the rubber gasket in it, inside it, and the other end of the pipe is just straight and slips right into there. But like all plastic pipe, subject to damage from heavy loading. So you've got to be careful about where you put this and how you install it. This graph here is kind of a useful thing uh, to have. It's obviously going to be in the materials we give to you, but it shows you the types of joints that are typically used and the kinds of pipe that they can be used with. And if you look at this, the sort of the most ubiquitous one is the rubber bell and gasket. So if you've got a question on an exam and you just really aren't sure, chances are if you pick rubber bell and gasket, you'll probably be right, or you'll have a better chance of being right than picking something else. But this is a good table to get familiar with and potentially commit to memory. So once again, just to make sure we're clear on this, that's the bell. That's the spigot, and that black thing on the inside is the rubber gasket if you're required to identify them in a picture. As I said, installation is critical, particularly with the plastic pipe. So we're going to talk a little bit about sort of the installation components or things to be aware of. We'll talk a little bit about installation. We'll talk about the bedding. We'll talk about backfill and the components and materials, which are going to kind of dictate how you do this. The bedding is what's supporting the pipe from underneath. The backfill is the dirt that is layered in on top. Wastewater pipes are typically put into excavated trenches. There are a ton of safety rules around excavation. Read up on your safety regs. We're going to be doing a safety session later on in the series, but it is really important that excavation be done correctly and safely. Every year there are wastewater and utility workers that get buried in cave-ins because the rules weren't followed. Obviously, other utilities have to be located. We mentioned water lines are typically in the streets. There's often other utilities, phone lines, things like that. So one call is your friend if you're doing work out there. Other utilities always have to be located before you do work. Typically, you're going to need 48 hours worth of notice. And it's really good to remember that if you do not use one call, you break it, you buy it. Whoever digs and potentially the employer and the person doing the digging can be liable for damages. And mistakes happen all the time. System I worked with a couple of years ago was having repeated backups in a section of sewer, and they found out that the phone company had driven a telephone pole right through their sewer line because they had done the digging without doing the one call. So be careful about that. Most excavations obviously going to be done with a backhoe or some sort of large piece of mechanical equipment. That being said, you are likely over time to run into trenchless technology more and more because it's becoming more affordable. So that's relining pipe instead of replacing it. Doing pipe bursting, which I talked about before, happens quite a lot these days on smaller diameter lines. Basically run a cable through, pull a gizmo through that breaks the existing pipe and pulls a new one in behind it. Boring and micro tunneling are often also done. Really important to read your manufacturer's instructions when you're doing pipe installation. Obviously, every manufacturer, even across different kinds of PVC pipe, is going to have their own specifics, and you want to make sure you follow the directions because the last thing you want to do is bury a big section of pipe and then have to dig it up. And it's really important when you're working with this stuff to be careful. Small diameter pipe, light or PVC pipe, people can pick that up. But big pipe, it should be moved with machinery. The last thing you want to do is crush somebody. Another thing that's really important to remember is that when you're assembling these pipes, the bells face uphill, upstream. The last thing you want is the water pouring into the bell. You want the wastewater flowing over the seal, not into it. So, if you were looking at a cross section of a pipe install, the bell is always going to be higher than the spigot so that the flow works the right way. Let's talk a little bit about bedding and backfill. Again, we're not going to go into the specifics. We're just going to talk about sort of the basic components. Um, Pipe has to be bedded for it to be correctly supported and to last as long as the manufacturer, indicates it's going to. We've run into situations where there's been incorrectly installed pipe that has led to premature failure. So pipe has to be bedded. It's typically bedded into compacted crushed aggregate. Which is sloped to the appropriate slope. Sometimes you'll see sand or pea gravel. If you use that, it has to be compacted because everything will settle over time, and you want the pipe not to move after it's been installed. It is really important if you're just using native materials, so the existing soil, that it's excavated to the appropriate grade for the slope that you need, and that it's compacted really well. You have to compact not only the bottom of the trench, but also the sides. Any load pushing down on the top of the pipe is going to want to make the sides flare out and make the pipe oval. So it's really important to compact all around the pipe so it's supported 360 degrees around. The compacting will directly affect the load that a pipe can carry. Again, it's how much you compact and the lifts or the depth of the compaction that you're going to do in layers is going to vary depending on the pipe you're installing. But it's good to know that compacting is required for the pipe to do what it needs to do. And if you're using that bell and spigot type installation, the bells are obviously wider than the rest of the pipe. So you have to take account for that and leave space to accommodate those bells so that they're not getting crushed. The backfill typically has three elements or three things that it's doing. It's protecting the pipe from moving, breaking, and crushing. Typically, you've got to compact it in layers. So if you've got an 8-foot deep hole, you don't just pour in 8 feet deep and compact the top and be done with it. It'll typically get compacted in what are called lifts. So a layer could be anywhere from a foot to a couple of feet. Again, read the directions for your particular pipe, but you're going to be doing that in layers until the trench gets completely filled, and then you're going to restore the surface. Talk a little bit about service connections. This is the piece that's connecting the houses and businesses to your sewer mains. Which are typically going to be in the street, or like I said, in my place, in the alley in the back. There's a lot of different ways that this can be done. Sometimes they're very shallow, as you can see on the picture on the left. Sometimes they are very, very deep. You can see the picture on the right where there's shoring in place to make sure there's no cave-in and keep the workers safe. Service connections are often called taps. Kind of the lingo that's used to describe them varies from region to region, but taps might be something that you see. And there's a lot of different ways that it can be done. Sometimes they're used clamp-on saddle tees to connect the service line to the main. Sometimes insertion-wise and tees are used. Sometimes it's actually glued to the pipe with epoxy or wedged in with a rubber wedge. The two important things to remember here is that connection between the service line and the lateral that it's going into has to be a tight seal. You don't want infiltration, or you don't want water or roots or anything to be able to get in, and you obviously don't want any sewage to get out. So it's really important that those connections be well maintained and well sealed when they're made. And it's also important to make sure that the service line connects to the pipe, but does not extend into the main, because the last thing you want is a big piece of pipe sticking out into the middle of the flow that's potentially going to trap materials and cause blockages. Let's talk a little bit about manholes. Every sewer line is going to need to be cleaned at some point. You need to be able to get in there, and you get in them through the manholes. They are typically installed in laterals, main trunks, and interceptor sewers for maintenance and cleaning access. They're going to typically be in places where sewers change direction, particularly if you're using rigid pipe. It doesn't go around corners, so you basically use the manhole as the corner. In places where there are elevation drops, so when the connecting pipe is much lower than the pipe that the flow is coming in on, and at junctions of multiple pipes. Um, they're also in straight runs. If you drive down the street, you'll often see manholes spaced apart. They're typically not going to be any more than 300 to 500 feet apart. And the reason for that is that you want your cleaning equipment to be able to get from one manhole to the next. So the spacing between them is going to be limited by the length of cleaning equipment. There are a lot of different ways manholes are constructed. Older ones are often made out of brick, where they were sort of placed in place by masons. Typically now, they're precast concrete barrels or made out of fiberglass. Here in New Mexico, the typical manhole is a precast concrete tubes with a poured in place base. Sometimes they've got steps, sometimes they've got a ladder. In cross section, they typically look something like this, where you've got sort of 6 main parts, and typically you're responsible for being able to identify what these parts are. So the base is typically going to be poured in place concrete. It's going to have channels to route flow, might be sloped. You've got inlet and outlet pipes. Sewage is going to come in at maybe multiple levels, and it obviously has to go out of the manhole as well. Those pipes have to be sealed, just like service lines have to be sealed to prevent leakage. They are going to have typically precast concrete or fiberglass barrels that are fit together. You can see in the image there, you've got sort of several rings to account for different heights. They're kind of modular. Each seal or each section is going to be sealed to the ones above and below it, again, to prevent infiltration or sewage getting out. There's typically a cone at the top, either concentric or eccentric. So where you're sort of moving down the side or where it's sort of completely cone shaped. There's going to be level adjustment rings over time as streets get paved and repaved. The level of the manhole needs to rise. And yes, we will be sending you copies of these slides. And so one of the ways you do that is with adjustment rings that are, a few inches in height to account for added pavement. And then, of course, you're going to have a tight fitting cast iron ring at the top with a lid because cars and things like that are going to be driving over it. And iron is very durable. Looking down, this is kind of what a typical sewer manhole might look like. You can see this one happens to have 2 entrances and 1 exit. And you can tell from the picture they're at slightly different height. The main flow is moving from the right-hand side of the image up to the top, but there's additional flow coming in from the bottom. You can see there. One thing I do want to point out, there's some rings in there for people to climb down. You can tell they're very, very rusty. Sewer gases are incredibly corrosive, so steps can deteriorate, things can get slippery. Be really, really careful when you're accessing manholes. They are what are called confined spaces. And have very, very strict regulations around entry that you should, under no circumstances, work around or avoid. Confined spaces are spaces that have limited openings for entry and exit. They have bad ventilation. And one of the things that can happen in sewers is that deadly gases can accumulate, or just the oxygen can be displaced. And if you go in there, without the right precautions, without making sure that it's safe, you might pass out and potentially even die at the bottom of a manhole. Happens every year. So be careful, understand your confined space rules, use gas sniffers and the appropriate tools and PPE. The other important thing about confined spaces is they're basically not designed for continuous work or occupancy. As I said, OSHA regulates confined space entry. There's a lot of regulations. We'll talk a little bit more about them in our safety session, but this is a whole topic unto itself. be aware that the basics of OSHA regulations are likely to be covered in your test. In New Mexico, for example, OSHA regulations specific to manholes are covered in the operator safety part of the test. So you are required to know about them.
James.
Yes.
Okay, yeah, we have a question and it might be going
Mhm.
right into your next section here, but how often do you service manholes?
It's gonna vary. I think every one of them is probably going to typically be looked at on at least an annual basis. But if you've got a problematic section of pipe, you might be there on a monthly basis or even more. So it's gonna kind of be a dependent on the requirements of your particular system. But what is really, really important is that when you service them, just like everything else you do in the water and wastewater world, it's a really good idea to document the fact that the service happened and what the conditions were. So, whether you're pumping sediment out of the bottom or you're in there to clean a blockage, um, you want to keep track of that because if you do, you'll see patterns develop. And the last thing you want to do is have to go deal with a blocked manhole or blocked sewer, having that be the reason for your visit. If you are documenting your O&M activities, you'll see patterns develop and you'll be able to deal with those regular operations and maintenance issues well before they become a problem that actually causes, sewage to back up into uh, somebody's place. So it's gonna vary. At a bare minimum, I think they should all be looked at least annually, because if you don't look, you won't know what's going on in there. But again, as you do your maintenance, document that very carefully. And if you've got questions about different ways to document that, feel free to reach out to us. The technical assistance part of this program annually means once a year. Um, but if you've got the ability to check more often, you should do that. A lot of systems will develop cleaning programs where they go around and proactively clean stuff out before it gets to be a big problem. Um, so while we're on the subject of cleaning, let's just talk about a couple of different things here. One of the things you're liable to run across in your exam is information about different types of cleaning techniques and materials. Um, can manholes come in bigger sizes? The depth varies considerably, depending on the situation, which is why they're modular. They're maybe different sized manholes as well. I mean, they tend to be typically standard. I think they're average about 6 feet in length, but this might be a question that's one of the other folks that's on the training here could throw out whether most of the manholes in your particular location are the same size. I know sort of modern construction, uh, they're they tend to sort of stick to standard sizes. There are definitely, yeah, different sized openings as well. And again, some of the construction of the manhole is going to depend on its function. Is it, for example, just a transition, or is it a manhole where maybe 3 or 4 different lines are coming together? Obviously, you would probably want that to be a little bit larger. Um, so as I mentioned, sewers, they get blocked, they require cleaning. We'll be talking about fats, oils, and greases and various other issues later on, but solids built up, those non-flushable wipes that everybody seems to flush down the toilet, root intrusion. A lot of maintenance has to be done on collection system to make sure that they operate efficiently. And the methods that are used vary quite a bit. Sometimes it has more to do with tradition than economics. But you are often going to see questions about different kinds of cleaning tools and different kinds of cleaning methods on your exam. So it's kind of important to have a good broad overview of the kinds of tools and the kinds of cleaning you might run into in your career, even though your particular system may only use a couple of these. And typically there are good diagrams and descriptions of these materials or tools and methods in training materials. The Sacramento State guides that we've talked about on a couple of occasions that we will talk about quite a bit as we go through this series have a lot of really good information in them and are worth reviewing. Sort of 4 main categories of cleaning that are typically covered. There's hydraulic cleaning, there's preventive maintenance, there's rotting, and then there's dealing with stoppages or blockages. So hydraulic cleaning is basically using a jet rotor, high velocity water to scour debris loose and move it to a manhole. So this is one of those things that is typically done as a maintenance thing. You don't wait until things get blocked. You periodically go clean the pipes out, move materials down to the next manhole, and clean it out. There's a lot of different sizes of these. They could be on a truck or a trailer, but they're typically going to have three components. There's at least going to be a water supply tank. There's going to be a high pressure pump and some sort of engine for driving it. The length of hose is going to vary, but a truck's typically got about 500 feet. And you notice that 500 feet kind of matches the distance between manholes, sort of the maximum length between manholes. You want to be able to at least get to the next manhole with your cleaning equipment. There are a lot of different kinds of attachments that you can put on these things for specific jobs. They're really good at scouring grit out and debris and grease. They don't necessarily by themselves do that great with roots, but a lot of them have mechanical root cutting tools that you can attach to them. So you're kind of doing two jobs at once. A key thing to remember is the direction that you're working. You're always working from downstream toward upstream toward the blockage, because basically if there's a blockage or if there's materials you're trying to bring down, you're bringing them down toward yourself so that you can pump them out. There are also hand rotters. The old-fashioned way of doing this is with a big long pole with a coil spring or a hook or something on the end. Typically, those aren't going to be anything longer than about 100 feet because there's only so much a human being can do. The sort of more mechanical version of those are the power rodders, which is essentially a steel rod or a cable. Works kind of like a power jet, except there's no water involved. It's just a cable with some sort of attachment that's spinning on a because of a motor. Those are typically truck mounted, but they could be trailer mounted. And if you're using one of these, you typically use the rotor and then you'll do some hydraulic cleaning afterwards. As I said, there are a lot of different kinds of tools. This is a set of pictures from those Sacramento State guides that sort of show you some of the different kinds of tools that you might use for different jobs. These specifically are hand rodding attachments, but the mechanical versions have similar kinds of tools attached to them. As I was saying, there's a lot of different kinds of rodding tools, a lot of different kinds of attachments. Which ones you use are going to depend on the blockage type that you're dealing with. And there are a lot of different kinds of blockage. We're not going to talk about all of them, but I do want to point out that fog, fats, oils, and grease, junk towels. It's amazing what people put into sewers, or what you can end up with if you've got a combined sewer where it has storm and sewer water going through it. If your particular system is dealing with a fog problem, feel free to reach out to us. One of the presenters that you'll hear in a later session, AJ Barney, he's an engineer. He's done fog programs for a variety of larger and smaller utilities. There's a lot of ways you can prevent this stuff from even getting into your system in the first place. And as we pointed out at the beginning, there is a technical assistance component to this grant as well. So if you've got some issues with fog, feel free to reach out with us and we can see if we can help you. On the subject of cleaning and maintenance, there's sort of three typical categories that they fall into, and you should be kind of understand what they are. There's preventive maintenance or preventative maintenance. There's emergency clearing, and then there's emergency repairs. So preventive maintenance is that cleaning that you're doing to avoid blockages. You're cleaning out the debris that builds up before it causes a blockage, before it causes a problem. This is things like, routine line cleaning, maybe doing chemical treatment for roots. If your sewer has root intrusion problems, sediment removal, things like that. Things that you do on the regular to minimize problems like backups and odors and lift station callouts. It's the basic stuff you do to prevent worse and bigger problems. Obviously, you can't avoid everything, so there's always going to be some emergency clearing work and emergency repairs. The basic difference between those um, is that emergency clearing is getting things out of the system, whereas emergency repairs will involve some sort of a failure of the system. So maybe a line break or a sewer line collapse. They're all about getting the system back into operation as soon as possible. Step one, obviously, is finding the best method to fix the problem. And this is, as I was saying, with the sort of basic visiting of manholes for cleaning, why it's really important to keep records, because if you keep maintenance records and look at them once in a while and analyze them, not only will you be able to potentially see where problems are happening, but you'll be able to identify what kinds of problems are happening, and over time, whether the interventions that you are using or the maintenance tools that are using are actually working the way they're supposed to. Sometimes you have to build a better mousetrap, and the best way to figure that out is to keep records about how the mousetrap you got worked. So keep those records and be able to identify sort of those three main categories: the preventive maintenance, emergency clearing, and repairs. When you're looking at this stuff, um, uh, particularly on the clearing and repair side of things, there's a lot of factors to consider about how you're going to approach the problem and whether you need to continue doing repairs and maybe want to move on to replacement. Things like your prior history, nearby trees. Did you suddenly have a problem arise because of a bunch of new connections? Were other utilities in the area doing work that might have caused your problem, like the telephone company I mentioned earlier? And also, be aware of the surface indications that might indicate something going on underneath the ground, like sinkholes, potholes, settlement, or indentations in places where pipes are at. So again, I know I'm kind of beating a dead horse here, but keep records of repairs and maintenance and make them useful and detailed enough so that you can understand what it was that you did. Record stuff that's important, where and when the issue occurred, what the cause was, the line size, the manhole ID that you were working out of, and the amount and type of material that was removed, because sometimes that can give you an indication of where it's coming from. We did some work a few years ago with Gatesville, Texas, which, among other things, has a bunch of prisons. And one of the things they realized by analyzing the materials that they were pulling out of their blocked sewers was that a lot of it was getting into the system through the prison. So they were able to, install some equipment to deal with that. But had they not sort of done that analysis and collected that information, they would not have been able to figure out where it was coming from. As I mentioned before, cleaning always takes place from downstream of the blockage. You're not trying to scuba dive and clean up at the same time. Obviously, if you're trying to clean a blockage from upstream, the upstream manholes are often full. It's really important when you're doing this cleaning to not, clean the blockage and then let it move further downstream and block it. So the idea is to have all your equipment there so that you can clear the blockage, pump it out of the manhole there, and move on. I mentioned at the very beginning the issue of septic sewage. The need for that, the reason we've got that airspace in our sewer line, and the reason we don't want it to typically run more than half full is because we want the bacteria that are in there doing their things to be able to continue to do their things. If you have large blockages and the pipes fill up, you may develop anaerobic conditions. And when that happens, the sewage can become septic, which can make the treatment of the sewage at the wastewater treatment plant much more difficult or problematic, and in some cases might actually overwhelm your system's ability to treat the sewage. So if there are large blockages in your system, it is a very good idea as you're dealing with them to let the wastewater treatment plant know what you're doing so that they can coordinate with you to plan for what's coming. They may have holding tanks where they can put some of this septic sewage, or they may want to change the treatment train a little bit to deal with that. But just recognize when you're dealing with large blockages, you want to be in communication with your wastewater treatment plant so that they can be prepared. We talked about lift stations in our early diagram there. This is an example of one kind. Lift stations are there to raise sewage up. Most of our sewer lines are going to be flowing downhill via gravity. As I mentioned, eventually you want to stop digging because it gets expensive to get more than about 10 or 15 feet below ground. So when you reach the end of a run, there will typically be a lift station that is going to pump that sewage up to a higher elevation so that gravity can take over again. Lift stations are very often covered in wastewater treatment operator exams. So you want to be able to understand what it does and be able to identify the different components and the two basic designs. So we're going to talk a little bit about components. We'll talk about some basic preventive maintenance and operation, and then the typical layout. So as I said, purpose, it's all about moving wastewater from low elevation to high elevation. They use pumps. They can use pumps to move water into force mains. So those are going to be the one exception of mains not being completely full. Force mains are under pressure. They are typically full. But after the force main does its thing, moves the sewage up to the higher elevation, the gravity sewer takes over again. The reason that you typically, again, have lift stations in your system is that at a certain point, it becomes too expensive to keep digging down to maintain the slope that you need for scouring velocity. Other reasons that you might have lift stations is because of soil instability. You know, the soil in your particular area just might not be conducive to digging deep trenches. You might have very high water tables in your area. So you don't want, you know, if you dig down below a certain level, you know, the trench is just going to fill with water, which you can't deal with. And it just might be an economical solution for current flow levels. The goal when they're designing a lift station is to basically move the wastewater with maximum efficiency, right? Lowest energy cost that you can. And Matt will be talking about pumps here shortly, but the whole idea here is to select pumps that fit your needs. You want to minimize surges and have constant flow because that provides less wear and tear on the system. The other thing about lift stations is they're often out in parts of town, in neighborhoods. They kind of have to blend in. So from an aesthetic standpoint, the goal is for them to blend in, for them not to be causing odors, to not make a lot of noise. You don't want a lot of trash around them. They can be a place to collect, bugs and vermin if they're not well maintained. So the idea here is, design them so that they blend in and maintain them so that they don't cause nuisances to your customers, because nothing like sewer smell to get customers to call the utility and say what's going on. There are two basic types of lift stations that are often discussed in wastewater treatment exams. There's what are called the wet well and the dry well. A dry well typically has two chambers. There's one chamber where the wastewater is, and there's another chamber that has all the mechanical equipment. So the pumps, the motors, the valves, and the controls. A wet well is a single tube, kind of like what I showed you in that image a couple of slides ago. It's a single tube where the sewage is in the bottom and the pumps are above the wastewater. There are benefits and drawbacks to either design. We're not going to kind of go into them right now, but there are some common things that you need to understand about the components in both of them. Lift stations are going to have pumps. Even a wet well, dry well system is going to have a wet well where the sewage is. There's always going to be hardware in there of some kind. They typically have bar racks, which are basically just coarse strainers to catch big materials. You might have a dry well. There's typically going to be some valves. There's almost always an electrical system associated with it because you've got to control the pumps. There will be alarms to let you know if there's a problem. If a pump goes down, motor shuts off. You have a high water issue. There's typically a motor control center that is sort of the brains of the operation that handles the pump controls and turns the pumps on and off based on the levels in there. There's typically a time recorder that lets you know how long the pumps have been running. And then typically there's going to be a force main because obviously you're pumping things out. It's not just going to squirt it off into the air. So the output of the pump will be a force main that will go somewhere, typically to a higher elevation where, again, it will go into a well or a manhole of some type where gravity will then take over again. Good to know these components. They might be called out. Another thing that's really important to recognize is that the hardware in lift stations is typically either high-grade aluminum or it's stainless steel because, again, like the rest of sewer systems, it's corrosive. It's always wet in there, and particularly in a wet well station. And the water can be corrosive. Again, hydrogen sulfide, other materials or components of the water can be very corrosive. So the metal components that are in a lift station are, again, typically aluminum or stainless steel because they don't corrode as much. Another topic that you might cover a little bit, it's typically not a very big section of the test, but it's really important, I think, for your career. And understanding how your system is put together, and that is maps. And by maps, I mean both physical maps and digital maps and as-built. So the diagrams of your system that the engineers will give you. There's typically two sets of construction project plans that you will see. There's a working plan that is used during construction, but nothing ever goes to plan. So there are always some deviations. So whenever a project is completed, what's supposed to happen is that a set of what are called as-built plans are put together that show exactly what got put in the ground and where. Those are the ones you want to have because those are the ones that are typically more accurate. They are basically, at least if they're done right, sometimes they're called as we wish they were built, as opposed to as built, but they become the true record of where everything is, where it's located. And they often have a lot of really useful information about, depth of bury, materials, when things were installed, sometimes, GPS coordinates, all sorts of stuff like that. And from these, you can build out, both paper maps and digital maps. They are your friends. If you've never looked at the as-built for your system, I highly suggest that you do. They will give you a very good understanding of the components that you particularly have in your system, how they're all connected, how the flows work. And the nice thing about as-built is, again, you can digitize them and you can take that as-built information and information from your work order system or your maintenance logs, and you can combine those together to start to see patterns about what's going on in your system. Got one more topic that we're going to cover very, very briefly before we move on to a couple of test questions and I hand things over to Matt. And that is I&I. I&I stands for inflow and infiltration. These are pretty much guaranteed to show up in some form on an exam. And it's really important to understand what they are and remember which definition goes with which. Inflow is water that is flowing into openings that are supposed to be there. So water that's maybe pouring into an open manhole, or maybe somebody's got what you thought was an inactive sewer connection that's actually working, or somebody's made an illegal connection. So that's inflow, sort of water going into a hole that's already there. Infiltration is water that's infiltrating into the pipe in ways that it shouldn't. It's sneaking in, right? So through cracks, you can see this is, I think, a London sewer, and you can see moisture well above the water level there. And that's because there have been cracks that are formed, and this is probably somewhere near the water table, and there's water flowing in areas that it's not supposed to. So inflow, water entering through manholes and illegal connections. Infiltration, groundwater that's going into the sewer through breaks and joints. The reason that it's important to keep track of these and make records of any repairs of these or instances where you notice that this is happening is because they can overload your wastewater treatment plant, or can result in an overload at your wastewater treatment plant. Because just like, if you've got a big backup and you suddenly clear it out, there's a big surge of water that hits your wastewater treatment plant all at once. Infiltration particularly, but inflow as well, can cause you to your plant to work outside its operating parameters. Your plant's designed to handle a certain amount of flow. Inflow and infiltration are not really part of that calculation, or at least not a substantial part of it. So if you've got, ongoing problems with inflow and infiltration, you know, repairs are in order. And one way to kind of look at this, just to kind of do a basic analysis of whether you might have this problem, is looking at your flows. Are you having massively increased flows at your wastewater treatment plant every time it rains? Might be an indication of infiltration or inflow. Other things you can look at is the drinking water use at your utility. Typically somewhere between 70 and maybe 80% of water that goes through our water distribution pipes comes back to this wastewater plant in the sewer. So if you've got a situation where there's more water coming back to the wastewater treatment plant than is going out, one of the reasons might be I&I. It might just be that you've got bad metering or other issues, but those are some sort of quick and dirty ways that you can kind of look at this. Identification can be very complex to particularly figure out, whether there are breaks in the system. You can do night surveys. For example, we know the high flow time is that sort of 10 to noon period. Typically, there's not much moving through your a typical, at least residential sewer system between the hours of 2 and 4 a.m. because most people are asleep. So if you are checking your manholes and there's a lot of clear water flow in that window, that might be an indication that you've got an inflow or infiltration problem. Seen situations where there's actually water main breaks that scour away water, and then the water's flowing directly out of the water main into the sewer and causing issues. So that's one good way to look. Obviously, CCTV inspection, particularly prior to line cleaning, is a way you can look for this. There's also smoke testing. And then the things I was mentioning before is that flow record analysis. Has there been drastic changes in flows at different times of year, or are you seeing drastic changes in your flow that are a result of weather events? There's a lot of ways to control it. They're all pretty much expensive. Slip lining, doing pipe replacement, chemical grouting, stormwater improvement. Typically, this is stuff that's going to require outside contractors, particularly if it's on a big system. Although collection crews can often deal with smaller joints and issues, raising rings, repairing joints, fixing deterioration, and things like that. If you've had a recent paving project and haven't raised the rings, or at least investigated whether they should be raised, check that out. I'm dealing with a system right now in Texas that had exactly that problem. The streets department went around and repaved a whole bunch of streets. And as a result, almost all of their manholes are actually below street level. So every time it rains, tons of water flows into the manholes. So they're trying to deal with that.
All right, and so you're seeing my screen okay here over here?
Indeed.
All right. So yeah, thanks so much. Collection systems are so fascinating. And it kind of forms the basis for our wastewater systems. It collects all of that waste, all of that flow, and it takes it to the treatment plant. And it's at the treatment plant, and it's on its way to the treatment plant where we look at mechanical systems. And so we have to get the waste to the treatment plant, like James talked about, through lift stations. But we also have to treat that waste. And so that's where mechanical systems come in. And so what are mechanical systems in wastewater? Well, it can range from everything from valves to compressors and generators. That's actually a generator over there. To pumps and motors, to compressors, to flow meters. Actually, that's a flow meter on top, and those are valves on the bottom. To blowers, to belt presses to dewater sludge, to mechanical solid separators, all the way up to chemical feed systems. And so what are we going to be talking about this afternoon? Well, it's going to be a limited agenda, and so we're going to cover some hydraulic basics, and then we're just going to get to some basics on pumps, and we're going to look at the basics on how pumps work. We're going to look at the type of pumps that you see in your wastewater system, and then we're going to talk about some operation and maintenance. And so we'll probably have another session on the rest of the mechanical systems and wastewater systems, and just cover pumps today. And so in order to understand how pumps work, we need to get back to the basics with hydraulics. And so hydraulics is all about, the force of liquids and their movement or their statics if they aren't moving within a system. And so the force of liquids is all about weight. It's a measure of weight, and it's pushing against all of those confining surfaces, be it in a pipe or some other thing that's confining it. And as you build on force, you get into pressure. And so this is force per unit area. And so we have pounds per square inch. You see this oftentimes expressed as PSI. And pressure increases with depth. With the height of the fluid, pressure increases. And pressure is a force that acts in all directions the same way. And so it pushes up the same way, it pushes to the side the same way, and down the same way. So it acts the same in all directions. A relative of pressure is head. And basically, the head is the distance from a free water surface. So that's like a water surface that's open to the atmosphere, and to a reference point below the surface. So it's the difference in those two levels in feet. And it also represents the height of the water column to be pumped. And head, when we talk about head, and we'll look at it in a minute, it also kind of is what drives gravity flow in a system. And we use gravity flow a lot in our wastewater systems and actually in our collection systems, as James has just taught us. As we build on our hydraulic basics, the next thing we need to take into account is velocity. And that's just how fast something's moving, the speed at which it's going. And, we think about that every day in our lives in terms of mile per hour. But when we think about water and wastewater, it's that distance traveled over time, and the units we typically see for it are going to be expressed in feet per second. And the way it's expressed here in all of these different ways, you should be familiar with the way these different units are expressed and the way they're abbreviated. And so when we take velocity and we add on to that, we get into flow rate. And that's the speed at which a unit of volume is moving. And so if we take a gallon of water and we make it move, it's the distance that gallon of water moves over time. And so we often see flow rates expressed as gallons per minute. All right. And we have instrumentation to read that. You can also see it expressed in cubic feet per second, or CFS, and in our big treatment plants, we see it expressed as million gallons per day. And so when we look at hydraulics, there's something you should be familiar with, and that's the hydraulic gradient line. And that's all about water seeking its own level. And so here I have down here, this ABCD, this is a pipe under pressure. And if I installed a vertical riser on this pressurized pipe, okay, the water would rise to the same level throughout those vertical risers. And that's going to be the hydraulic grade line, okay? Now, static head in the hydraulic grade line, all right, static head is the pressure due to elevation differences, okay? And so water likes to move downhill. It likes to move by gravity from a place of higher elevation to a place of lower elevation, okay? And so from a place of a higher hydraulic grade line to a place of lower hydraulic grade line. And that's how we design our gravity sewers. In this case, the static head, that difference in elevations is about 2 feet right here. From the higher elevation to the lower elevation is 2 feet. All right, another part of hydraulics is dynamic head. These are losses in head due to the movement of water that flow through the pipe. As water moves through pipe, it loses the dynamic, it loses head, it loses pressure. This, of course, is dependent on fluid type. You know, is it water? Is it wastewater? Does it have a lot of solids in it? Does it not have very many solids in it? It's dependent on that density, that viscosity, and how fast that water is moving. The faster it moves, the more dynamic head you have, the less pressure you're going to have, the more you're going to lose. And also, you know, there's two parts of dynamic head, two parts of those losses, and one is those friction losses. You know, as these fluids move through the pipe, it rubs up against that pipe. All right, it causes friction, and that causes it to lose head. And the rougher the pipe is, if you're in a concrete type of pipe, you're going to be a rougher pipe type. Friction losses are going to be higher than if you're in a PVC, like a smooth pipe or an ABS type of pipe. You also have what's called minor losses, and these are due to changes in pipe size, pipe shape, or direction. And so every time you change the direction of the flow in an elbow and a T, you know, as every time it goes through a valve, you lose head. Okay. And so these head losses are expressed as K factors. And you can see that these K factors are different for a big bend, for a little bend. You know, big bends have more, you know, friction loss in them than smaller bends do. And so these K factors, they fit into an equation. And so you can actually calculate what those minor losses would be in your system. The more you change the direction, the more losses you're going to have. So total dynamic head, it's a combination of things. It's the static head, those differences in head due to elevation, and dynamic head, those head losses due to friction losses and minor losses. Okay, so it's the total equivalent height that a fluid needs to be pumped, including dynamic head losses and what's already there, the static head. And so you can see I have a pump down here, all right, and I need to move it from this level all the way up over here, okay? And so that's an elevation difference. So the difference in those heights is due to static head, all right? And then the rest of the height are my head losses due to friction losses and minor losses. And so I need to have a pump that's able to push water all the way up to this upper level. All right. And so that's total dynamic head. It applies an energy or force to lift water from a lower elevation or level to a higher elevation or level. And we call this pump head. That's another thing that we call it. Or you might see it on a pump expressed as PDH, pump dynamic head. All right, so now that you have that basics on hydraulics, we're going to talk about pumps. How do you classify pumps? Well, it really depends on a few factors. The first one is on the character of the material you're pumping, as well as on the material size. And so raw wastewater has big material in it, big size material. And so you're going to need a different pump than you're going to use for grit or effluent or even sludge. Sludge is very thick and viscous, and so you're going to need a different pump type if you're going to be moving sludge. Also, when you're classifying pumps, you're going to have to know about the pumping conditions. Are you having to do a high lift? Is it a low lift? Do you need to move a lot of material, a high capacity of material? Or are you recirculating stuff within like a sludge basin? Principle of operation is also important. All of these pumps operate based on different principles, and we're going to be looking at all of these different principles of operation. There's the centrifugal principle, propeller pumps. You're going to have reciprocating pumps and turbine pumps. And so that's all different types of ways that these pumps move material within a wastewater system or treatment plant. Let's look at the pump family tree and see how all of this kind of flows into one another. And so at the very top, you got grandfather pump, all right? And so pumps can be classified as dynamic. And this is where the centrifugal pumps lie. Centrifugal pumps are all about high flow, low head. That means a lot of material movement with low pressures. Radial flow pumps are what most of us are used to when we look at centrifugal pumps. And flow is radial out the impeller head, but you also have propeller pumps, which move things axially along the pump shaft. Okay, and so those have a use as well. On the other side of the pump family tree, you have displacement pumps. Okay, displacement pumps are all about low flow, high pressures, high head. Okay. And so the different types of displacement pumps, on one side we have the rotary pumps, and these are going to be like piston pumps, which are used for moving sludge. It could be a peristaltic pump, which is used for chemical dosing. It could be a screw pump, which can be used for moving chemicals. It can be used for moving wastewater. It can be used for moving sludge, or progressive cavity pumps. And progressive cavity pumps is another type of positive displacement pump that we'll look at. On the other side of rotary, we do have our reciprocating pumps. And the primary type of reciprocating pump that you're going to see in wastewater is going to be the diaphragm pump. It's a chemical dosing pump that you're going to add chlorine as part of tertiary treatment. So where are pumps found in wastewater systems? And so centrifugal pumps. Okay, I'm going to be representing centrifugal pumps with this type of symbol. Centrifugal pumps, again, remember that's high flows, low head. We're going to see that in our raw wastewater, primary sludge, effluent wastewater, flush water, spray water, seal water. Positive displacement pumps, that's going to be our primary thickened and digested sludges. That's going to be in our slurries and also in our chemical feed applications. And so progressive cavity, I also am classifying them under as positive displacement because I see that's where they fit most. But if you know why they're in their own category, go ahead and chat me and let me know. But for now, I'm putting progressive cavity pumps under positive displacement category. Okay, so centrifugal pumps, we're going to talk about how they work, why it works, and it all comes to the centrifugal principle. And so basically all moving bodies, and that's me, that's you, that's water, that's a horse, we all want to travel in a straight line. Okay, but when moving bodies are forced to travel in that curve, we always want to swing off at a tangent. We always want to fly off at a straight line from the curve. All right, and we can see this nice example here. Here we're moving in a circle, and then no, we're not moving in a circle anymore. We're moving off on a tangent. Okay, that's all about the centrifugal principle. So centrifugal pumps, they work by the same principle, okay? It pushes water that's rotated in a circle away from the center of rotation. And so with centrifugal pumps, you'll see the fluid inlet is at the center, all right? And then we have an impeller that pushes that fluid out from the center into your casing, into your volute, and out into your system, okay? And so we see a lot of centrifugal pumps in our wastewater systems. Let's look at the different parts of centrifugal pumps. Okay, so there's our impeller in the center right there. I'll get my laser pointer out. There's our impeller. Okay, we also have our shaft. This shaft connects to the motor. All right, and we want to protect that shaft from corrosion and abrasion, so we oftentimes use sleeves to do that. We have bearings in this part of the pump that the pump rotates on. It gets rid of friction, allows the impeller to rotate freely. There's a coupling flange over here. You can't see it, but we need to be able to connect the pump to the motor. We have our suction piping on this side, and so we would have suction of material into the pump, into the center of that impeller, and it's going to be pushed out the top of the pump. The volute is the pump casing, and so that's what surrounds the impeller. We have wear rings, and those prevent internal leakage, and so you'll see that over here. That's a wear ring. And then packing and stuffing boxes. That's over here. That keeps air from being sucked into the pump and from pushing too much water out of the pump. And so we have two different types of shaft seals that we can use. One is with a stuffing box. All right, and so we see that here, and we can see that there's the packing gland on each side of the shaft. So this is the shaft going through the stuffing box. We have our packing gland that keeps the packing in place. There's the packing, and so this is a material that is used to, keep the pump all together, to keep water flow in and air from coming into the pump. And we have to replace this once in a while. We have to adjust this once in a while if we're getting too much material too much water leaking out of the pump or too much air going into the pump. And then we also have lantern rings, and lantern rings are right here. Okay, they protect by letting water and pressure in to the shaft and keeping dirt out. They help assist with cooling, and they use water to lubricate at the same time. And so we have a water coming into the packing ring here, or into the lantern ring, and it helps lubricate and cool that shaft, because as that shaft rotates, we're getting friction. And we want to make sure that things don't get too hot, or else, that shaft is going to seize up and the pump is not going to work. Besides the shaft seal with the packing, we also can have a mechanical seal. And so here is the shaft here. Okay, and so basically it's two highly polished seal faces that create a watertight seal. And so on one side you have a polished surface here in the seal ring, and on the other side you have a polished surface on the rotary side of things. And so this keeps the seal. It allows a certain amount of water in that forces the seal apart and allows rotation, but it also helps cool, and it helps it helps things so that they're not pushed together and too much friction. We see friction loss and centrifugal forces within this area keep the seals from leaking too much, but we will see some leaks going on both with a packing seal as well as a mechanical seal. When we look at centrifugal pumps, we have two types of impellers that you might see in wastewater systems. And so you'll have that open radial impeller type. They have larger open flow paths. This is going to be better for large solids, and they operate at lower heads and lower efficiencies. Okay, and so they're not going to move as much material. It's going to cost a little bit more energy, and we see that with our raw sewage pumps. They're not as efficient, and we have to use more energy to move that material. The other type of impeller type that we see in wastewater systems are closed radial. Okay, and so the vanes, here are the vanes down here, they're covered by shrouds on both sides. The flow paths are enclosed, and if you're trying to pump large solids with these, then they are going to clog. They're more likely than the open radial design. The types of centrifugal pumps that we're going to talk about and the types that we see in our wastewater treatment plants, we see our in-suction pumps, horizontal split case, vertical wet well pumps like you might see in a lift station with a wet well. You've got vertical multi-stage, vertical turbine, submersible non-clog that we use for pumping raw wastewater, and then submersible grinder type pumps. And so those are special types of submersible centrifugal pumps that have like a grinder in it to grind up waste into smaller chunks. so that it can move through the system. This is what a in-suction pumps looks like. It's typically what you would see in a wastewater system, and you can see this is the in-suction end here. Okay, that impeller spins and forces it out the other side. There's our shaft that goes to the motor. There's the packing gland, and the bearings are all right in there. This is for low flow, low head applications. Vertical discharge, okay, or rotate to where want the discharge. And so this part up here, you can't see it because my cute little icon is in the way, but that this volute here can be rotated away from vertical, and it can go off to the side if you want discharge off to the side. Here's an example of a in-suction centrifugal pump in a wastewater system. You can see that this is the suction side. This is the volute. Again, we have output out the top here and the motors over here. And so you can have these in-suction type of pumps. They can be close coupled and mounted directly to a motor, or they can be frame mounted like this one is, and have a shaft that goes between the motor and the pump, and it'll have a coupling in between. These people consider them to have more complex piping arrangements because of this offset discharge. It's not a straight through type of system. Horizontal split case, these are for high flow, low head applications. And they can be multi-stage with more than one impeller. In this case, we have just one impeller, and you can see that we have bearings on each side, and it's called split case because this top casing can be removed. It has that open back design. A lot of people like these because they're straight through flow for easy piping. But the problem with it is that they can take up large footprints. And this design here, this horizontal design, can be vertically mounted to decrease that footprint size. And so here's an example of that. This is actually in a drinking water system because you can see by the blue pipe. But this is a horizontal split case pump that's mounted vertically. And this is what it looks like when it's pulled apart. And you can see this is a multi-stage. It's got two different impellers to increase output and increase pressure. Vertical wet well pumps, this is what you might see in a lift station. Again, it's going to have the vertical shaft, and the motor is going to be up on the top of that shaft, and it's going to be suspended from the discharge piping. It has large openings, full-size openings for the passage of solids, and full-size passageways in the impeller and casing so that you don't get clogs when you're moving wastewater. It's usually used for shallow sumps or in wet wells of lift stations. All right, this is a vertical multi-stage pump. And really, you might see these more likely in drinking water systems because it really needs a clean water application for these to work. It really is used for low flows and high head. And the way that it gets that pressure up to get that head up is it has multiple impellers. They're just stacked on top of each other. And so we get flow in through here. They go up, pressure and head are increased as it moves up through those impellers and down through and out. And so it's a small footprint, straight through flow for easy piping installation. They're durable, long lasting, and nice workhorse pumps. Another type of centrifugal pump that you're going to see are vertical turbine pumps. The pump bowls down here, the casing, the impellers, the shaft, they're submerged in water at the end of the column pipe. The motor is mounted on top. Multiple impellers staged at the end of vertical shaft can create higher flows and higher pressures. And water flows into the bottom here. You can see there's a screen, and it comes up this pipe, and it flows out through the top. You're going to see these more commonly in booster pump stations or wells for drinking water systems. but I just wanted to mention them because you should know what they are in terms of, centrifugal pumps and how they fit in. Another type of centrifugal pump that we talk about in wastewater systems are propeller pumps. And so you have a propeller instead of an impeller at the end of the shaft, you have a propeller. And that propeller, as it rotates, it creates axial flow up the shaft, out the discharge tube. And we use them a lot for recirculating activated sludge in process tanks. We also have our submersible non-clog pumps. Okay, these are high flow, low head pumps. They're for solids handling. They're for the raw sewage. We want 3-inch solids and up. They don't get clogged easily. That's why they're called non-clog pumps. They're low efficiency, so they're going to use a lot of energy to move the material that they do move. And they have to be submerged. And so this end is submerged. Water is pumped in there and out. Submersible grinder pumps, again, low flow, high head pumps. These are going to be smaller, typically less than 16 horsepower. You might see these types at some lift stations if you need to process material and get it down to a smaller size before you pump it into the force main. And you also see some systems that have small residential units under 200 gallon per minute. And so every home will have a little grinder pump. Water comes in through here. There's a float. As it activates the float, the pump's turning on, it's going to grind and it's going to send out the water through this outlet. And that's for if you're pumping directly from a resident into a forced main. And so these tend to have a lot of issues. The homeowner has to take care of them. And so if you're able to not create a wastewater system or a collection system with a bunch of residential units, you'll be better off for it. And there's a grinder at the bottom of these types of pumps. And it basically grinds it down to between 1.25 inches and 2 inches in size. So you can force it into a small diameter force main. All right, well, I see that we are at 3 o'clock Mountain Time, 4 o'clock Central Time. So we're going to wrap it up. We're not going to go ahead and go overtime and be aware everybody has other things to do today. We're going to take up pumps and mechanical systems down the road at another webinar.